Indexing techniques in vector databases. Description. Methods used to organize and manage vectors in vector databases for efficient similarity search and retrieval. Techniques. Name. Flat brute force index. Description. A straightforward approach where all vectors are compared against the query vector using a chosen distance metric. Characteristics. Simplicity. Easy to implement. Accuracy. Provides exact results. Performance. Can be slow for large datasets. Use cases. Small data sets. Suitable for smaller datasets where performance is not a concern. Example. Import FICE. D128 dimension of vectors. Index FICE. Index flat L2 DL2 distance metric. Vectors NP. Random. Random 1000. D. As type float 32. Index. Add vectors to the index. Name. Inverted file IVF index. Description. Partitions the vector space into clusters and assigns vectors to these clusters. During search, only relevant clusters are examined. Characteristics. Scalability. Scales better than brute force for large datasets. Efficiency. Reduces the number of comparisons needed. Complexity. More complex to implement and tune. Use cases. Large data sets. Suitable for large datasets requiring faster search times. Example. Import FICE. D128 dimension of vectors. NList 100 number of clusters. Quantizer FICE. Index flat L2D base index for clustering. Index FICE. Index IVF flat quantizer. D. NList. FICE. Metrical 2. Vectors NP. Random. Random 1000. D. As type float 32. Index. Train vectors train the index clustering. Index. Add vectors to the index. Name. HNSW hierarchical navigable small world graph. Description. A graph-based index that builds a multi-layer graph for efficient nearest neighbor search. Characteristics. High performance. Provides fast search times with high accuracy. Memory usage. Can be memory intensive. Complexity. Complex to implement but highly efficient. Use cases. Real-time search. Ideal for applications requiring real-time search capabilities. Example. From HNSWLIB import index. D128 dimension of vectors. Index spatial 2. DIMD. Index. Index max elements 1000. EF construction 200. M16. Vectors NP. Random. Random 1000. D. As type float 32. Index. Add items vectors. Name. Annoy approximate nearest neighbors OYE. Description. Uses multiple random projection trees to partition the vector space in approximate nearest neighbor search. Characteristics. Speed. Fast search times with good accuracy. Simplicity. Easy to implement and use. Approximation. Provides approximate results. Use cases. Recommendation systems. Useful in recommendation systems and scenarios where approximate results are acceptable. Example. From Annoy import Annoy index. D128 dimension of vectors. N trees 10 number of trees. Index Annoy indexed. Angular. Vectors NP. Random. Random 1000. D. To list. For I. Vector in enumerate vectors. Index. Add itemy. Vector. Index. Build N trees build the index with specified number of trees. Name. Product quantization PQ. Description. Compresses vectors into smaller codes and performs approximate nearest neighbor search using these codes. Characteristics. Compression. Reduces the storage requirements. Efficiency. Efficient search with a balance of speed and accuracy. Complexity. Requires careful tuning for optimal performance. Use cases. Memory-constrained environments. Suitable for environments with limited memory resources. Example. Empath-FICE. D128 dimension of vectors. M8 number of subquantizers. NBITS 8 bits per subquantizer. Index FICE. Index PQD. M. NBITS. Vectors NP. Random. Random 1000. D. As type float 32. Index. Train vectors train the index. Index. Add vectors to the index. Considerations. Data set size. Description. The size of the dataset can influence the choice of indexing technique. Larger datasets may benefit from more advanced techniques like IVF or HNSW. Query performance. Description. Consider the trade-off between search speed and accuracy. Approximate methods like ANOI and PQ can provide faster results with some loss in precision. Memory usage. Description. Some techniques, like HNSW, may require more memory. Choose an indexing method that fits within the memory constraints of your environment. Implementation complexity. Description. Advanced techniques may offer better performance but can be more complex to implement and tune. Balance the need for performance with the available resources and expertise.